In this video, we're going to look at multinomial coefficients. Now we're going to start with a definition, really. The multinomial coefficient, which is this sort of bracketed notation here, you can see. Now this is the coefficient of x1 to the power of k1, x2 to the power of k2, xm to the power of km in the expansion of x1 plus x2 plus ... all the way up to xm to the power of n. And this follows where k1 plus k2 plus ... all the way up to km is equal to n. So this is basically an expansion of the binomial coefficients that you'd have when you were squaring some brackets. Here we have brackets with m terms inside the brackets raised to the power of n, and then this multinomial coefficient, which is defined by n factorial divided by k1 factorial times k2 factorial multiplied by all the way up to km factorial, gives us the coefficient of x1 to the k1, x2 to the k2, etc. up to xm to the km, wherever k1 plus k2 plus ... up to km is equal to n. This is easiest to see if we're looking at an example. So, e.g., let's look at in the expansion of x1 plus x2 plus up to x4, so that x3 plus x4, I'll just write this all out. So we have 4 terms into the bracket, inside the bracket. We're going to raise it to the power of 5. So in this example, what we have m equals 4, n equals 5. The coefficient of x1 squared, x2 to the power of 0, x3 to the power of 1, x4 squared. Notice that all of these powers add up to 5, which is necessary. The coefficient of this is given by the multinomial coefficient, so it's n factorial, that's 5 factorial divided by the factorial of all the powers multiplied together, so it's 2 factorial times 0 factorial times 1 factorial times 2 factorial. 5 factorial is 120. 2 factorial is 2, 0, so it's 2 times 1 times 1 times 2 at the bottom. This is 4 at the bottom. This is equal to 30. So obviously, this is a lot quicker than just doing that long expansion. Similarly, using the same expansion, if we were asked for the coefficient of x1 to the 1, x2 to the 1, x3 to the 1, x4 squared. Again, all of these powers add up to 5. This is 5 factorial, that's my n factorial, divided by 1 factorial, 1 factorial, 1 factorial, 2 factorial, which is the same again, 120 on top, and now at the bottom this is just 2. So my coefficient here is 60. Okay, so that's sort of the definition of multinomial coefficient. Apart from expanding brackets, this comes up in a lot of places in probability. lots of different examples that you might see it used. One of the most common is the number of distinct permutations. Let's write down, e.g. the number of distinct permutations of n elements where some elements are repeated. Okay, and we'll use the word multiplicity. That's sort of the number of times it's repeated of element I is given by ki. Okay, again, now to put these sort of words into a solid example, e.g. how many permutations, or I suppose distinct permutations, how many distinct permutations are there of the letters of the word reference? So this is quite a nice one to look at because we clearly have repeated letters. So let's think about this question. So we have, let's look at R. We have two R's. So that's going to be my K1 is equal to 2. Let's look at the E's. We have 4 E's. So my K2 is equal to 4. F, we have 1 F. So K3 is going to be 1. And we have 1 N. And we also have 1 C. And notice that K1 plus K2 plus K3 plus K4 plus K5 is equal to 9. This is N, the total number of letters. Okay, then permutations. We just need the multinomial coefficient. So we're going to have N, K1, comma K2, K3, K4, K5 equals, well, N is 9 and K1 is 2, 4, 1, 1, 1 equals, well, 9 factorial over 2 factorial, 4 factorial, 1 factorial, 1 factorial, 1 factorial equals the actual, so the denominator here I think is 2 times 24, so it's 48. This is 9 factorial over 48. 9 factorial is 362880 and divided by 48. That gives me 7,560 permutations. So 7,560 different permutations of the letters of the word reference.